to get started on our training today. And we're going to be talking about common compressor concerns. What we see in the field, different types of compressors, so on and so forth. So let's start with today's agenda. Got quite a bit of information. First, we're going to run through quickly the refrigeration cycle. Everybody should know that, or at least gone through some training for it, especially here recently. We're going to talk about the different types of compressors, where we see them, what they're used for, and a little bit of breakdown of each. The causes of compressor failures. The found failures from manufacturers, which I found to be enlightening. So I'd like to share that with everybody, courtesy of Cook and Carrier and Emerson Technologies. The different types of oils that used to be used, oils that are used now, and oils that may be used in the very, very near future. We're going to talk about some troubleshooting, some questions, some things that we want to look at. And then prevention. How do we stop these things from happening? Or what do we look for to prevent these things from happening? So the refrigeration cycle, we got our different components within that cycle. Of course, the first is the compressor, which is what we're going to be discussing today. And that compressor compresses vapor refrigerant. So as it gets back to the compressor, okay, we want it to be fully in the vapor state. And then what it does at that point is it decreases the volume, which will increase the pressure. And it heats up due to compressing that vapor to a liquid. The next one here is the condenser. And what it does is it condenses it at its saturation point. We have high pressure at that point and a warm temperature. And we call that subcooling, or known as our liquid saturation, or LSAT if you see it on digital gauges, things like that. Again, Josh Elliott did a lot of training on this recently, so not spending a lot of time on it, just running through it. And then we have our metering device right here, as in this picture is showing, and that there's a TXV. What happens here is the pressure decreases at that metering device. It goes from a low pressure and low temperature. It's mostly liquid still, about 80% or so. And we call that flash gas. What's flash gas? Well, it's a refrigerant in a gas form produced spontaneously when the condensed liquid is subjected to boiling. And again, usually that's right after that metering device. Evaporator, once we get through our metering device here, it's warming up the liquid and it boils it at that saturation point. It's a low pressure and low vapor temperature. And that is known as our superheat or vapor saturation. We have our suction line, our liquid line, which is where we check our temperatures and compare for our superheat and subcooling, and then our discharge line. Biggest thing that I want everybody to know is that as that refrigerant comes out of that compressor at the discharge line, 300 degrees Fahrenheit is our recommended max. Some manufacturers recommend a little less, but keep in mind if you want to check that temperature there, you can. And that is 300 degrees max coming out of that discharge. All right, so let's jump into the different types of compressors that we'll see out there that we may or may not see, depending on what we work on. So the first type is the reciprocating compressor, or as some people call it, the piston compressor. This used to be pretty common in our systems that we'll see. It's a back and forth piston motion, okay, as you see right here in a cylinder that's synchronized with suction and discharge valves. You see our suction here, our compression part, to compress vaporized refrigerant from a low pressure and temperature to a high pressure and temperature. The motion is achieved by a crankshaft right here, which converts the motor rotations to piston reciprocations. Household refrigerators, freezers, welded hermetic type would be where you would see these. And also in the residential and commercial realm in air conditioning and refrigeration applications. These are open, semi-hermetic, and welded hermetic types. So those are the different types that you will see of these reciprocating compressors. The next one is a rotary vane compressor, or rotary piston, is what it's also known as. This has a fixed casing known as the cylinder right here. The vane splits the space between the cylinder and the rolling piston into two sections for our suction and our discharge. As that rolling piston rotates, the two volumes are increased and decreased to achieve the gas suction, compression, and discharge. These right here, you'll typically see with an accumulator attached to them. These are smaller capacity applications, typically of 5 tons or less, refrigerators, freezers, residential air conditioners, and heat pumps below 5 tons as well. Our next one is a rotary scroll compressor, which we see quite a bit of now. It's becoming more and more common in the residential realm. And these are used to compress larger volumes of gaseous refrigerant to a higher pressure and temperature via fixed and orbital scroll. Emerson has a nice one that actually is a swing scroll compressor, which we can always talk about at a later date, but it's really nice to see their new style that prevents less wear and tear on the internal of the compressor. The cool vapor refrigerant is drawn in from outside the fixed scroll. Then it's compressed in between the fixed and orbital scroll. And finally, that compressed refrigerant is discharged from the center of the fixed scroll with a continuous displacement. These compressors we'll typically see in commercial and air conditioning commercial air conditioning applications, refrigeration applications as well. And these are capacities of 5 to 10 tons. You'll actually see this type of compressor here in the new Carrier Evolution or Bryan Evolution Carrier Infinity 5-ton Green Speed Extreme. Couple different types of compressors that we may not see too much unless we get into the industrial and commercial applications. And the first one here is a rotary screw compressor. And just like the name suggests, it's made up of 2 intermeshing screws or rotors. It uses these rotors to compress large volumes of gaseous refrigerant to a high pressure and temperature. The compression's performed by male and female rotors that reduce the refrigerant gas volume as they rotate. The cool vapor refrigerant then enters the suction port, is forced by the meshing rotors through the threads as the screws rotate, and exits at the discharge point with high pressure and high temperature. And these applications, again, are going to be commercial, industrial air conditioning and refrigeration systems of 20 to 750 tons. The final type of compressor that we'll talk about today is a centrifugal compressor, or a turbo or radial compressor, are also other names that you'll hear it go by. This compresses refrigerant to a high pressure and temperature by adding kinetic energy to the cooled vapor refrigerant. It does that by these rotating impellers. The cool vapor refrigerant is forced to pass into and through the impeller, and the impeller forces the fluid to speed up faster and faster. The high-speed refrigerant gas is then forced to pass through the diffuser, where the refrigerant gas volume expands and speeds as its speed decreases. This process converts that kinetic energy of the high-speed, low-pressure gas to a low-speed, higher-pressure gas. The higher the impeller speed, the higher the pressure. These are going to be commercial and industrial applications of 200 plus tons. So may not run into too many of these. Now, as we went through all of those, you may have seen that, again, it's going from a vapor, low pressure vapor, to a high pressure liquid or heated up. So what causes these compressors to fail? Well, lubrication or lack thereof. Overheating, excessive heat. Sure, we've all ran into a compressor that's overheated. Could be an electrical short. Could also be misassembly from the manufacturer. And we'll talk about some statistics that we have from that was presented by Cook and everything. So from the manufacturers, what do they see versus what do we see? Well, we out in the field, we diagnose, again, most of the time you can see here, it's an electrical failure. Very, very small amount do we ever say that it's mechanical. And what happens when we send that back to the manufacturer for them to diagnose it and see what's going on? Well, it's the complete opposite. It's typically a mechanical failure, very rarely an electrical failure. So let's talk about some mechanical failures. The first one we're going to talk about is lack of lubrication. And, dilution, washout is going to be one of those. And those are in a couple forms of what we call liquid floodback. And liquid floodback occurs when liquid refrigerant enters the compressor's crankcase during the running cycle. Take anything from this here, liquid floodback is during the running cycle. Refrigerant floodback will dilute the compressor's oil with liquid refrigerant. And when that happens, that's going to cause the oil in the crankcase to wash the bearings clean of their lubrication oil or lubricating oil. This same phenomenon can be also pressurize a compressor's crankcase, causing leakage around rings, valves, and other compressor parts and passageways. So if you ever run into one where it's leaking around one of these valves, compressor valves or rings, you could have liquid floodback occurring. The other one is flooded start. Flooded start is refrigerant vapor that migrates to the compressor when the compressor is off. Liquid floodback during the running cycle, flooded start when the compressor's off. So again, put it down here one more time. Floodback, compressors running, flooded start, compressors off. So just think when it starts, it was off. That's when we had our flooded start. Flood back is when it's running. Some other mechanical failures. Overheating. What causes overheating? If we have low suction pressure. Low suction pressure can come from a couple things. Low indoor airflow. It can come from a low refrigerant charge. If a system's low on refrigerant, how did it become low on refrigerant? Well, typically it can be a refrigerant leak, or it can be we're constantly putting hoses on the system, refrigerant gauges on the system. Especially if it's a critically charged system, over time, you're going to take refrigerant out of that system and can result in a low suction pressure, which can lead to overheating. That's why it's very important to consider putting refrigerant gauges on before you do every single time. High superheat. Could be different things that lead to high superheat. Again, it can be the same thing with low indoor airflow, low refrigerant charge, restrictions, things like that within the system. High discharge pressure. If we have a high discharge pressure, we can lead to floodbacks, things like that on the system, on that compressor. You can also lead to increased temperature on your discharge line, which again, what's our maximum number that we want to stay under? Anybody?
300, right?
300.
300. Good job. Yep. So you can always use your wireless probes, put it on your discharge line, put your system back together, check it when it's operating, and you can see what that discharge temperature is. Now, make sure your discharge, or make sure your wireless probes go up to that temperature, but that's one way to check that. So you can also get high discharge pressure with low outdoor airflow. Maybe a condensing fan motor is not running at the proper speed. If it's a variable speed fan, maybe it's stuck in a low speed or something, or the outdoor system or outdoor coil is dirty. Do we ever diagnose dirty systems? Nope, not at all. We want to clean them first, let them dry, check them, and then diagnose. So if you ever run into one and you're out on a no cooling call and you see that the system's dirty, you have to educate the client, the homeowner at that point that, you know, unfortunately, I can't diagnose this without properly cleaning it, and give them the solutions to cleaning it before diagnosing. You can miss things. Let's jump over to the electrical failures. Electrical failures, contactors. They could be chattering. They could be welded and or pitted. Again, while we're doing regular maintenance, if you notice these things, educate the client and suggest getting it replaced before we have an electrical failure of the compressor. Capacitor. Do we check a capacitor under load or not under load? What's the best way?
Under load.
Under load if at all possible. Thanks, Max. How do we check a capacitor under load? I didn't put the formula up here, but you can use the HVAC School app, and you can input the information. How do you check it, Max?
I just use the math, which is I take the amp draw, multiply by 2652, then divide it by the voltage.
Beautiful answer. Good job, Max. That is what we want to do. So to repeat what he said there was take the amp draw of the motor that you're checking, in this case, the compressor. You take that, you multiply it by 2652, which is a constant. Once you get that number, you will divide it by the voltage between for your compressor. So you check that across your capacitor from the hermetic to the common. And that will give you your microfarad reading. Do the same thing for the fan motor. So low microfarad bad capacitors can lead to overworking of those motors. It could be a low voltage issue. It could be electrical spikes, especially on these inverter systems and these higher end compressors, these modulating compressors, these multi-stage compressors. It is a very good idea to consider some sort of surge protection to help prevent some of these electrical spikes. So failed compressors that have been returned to Copeland. And this is the percent that we see here that are actually failed versus non-failed. Compressor faults found. So of those that failed or had faults, 26% are compressor manufacturer issues. So this purple right here is showing and representing the manufacturer issues that they have. So about a quarter of them. 12% is other manufacturer issues. So they equate to about 38%. However, 60% of them are misdiagnosis of field issues or other things that were done in the field that didn't prevent the compressor from failing. 2% user issues. So what's staggering is we have 60% being field issues out there. I would like to think that we're better than that too. So just be careful of how we check these things. The top 6 return findings, again, courtesy of Emerson, right here, almost 30% of them returned, no faults found at all. Less than 20% is debris internally in the system. 14%, 13% or so here is the drive bearing. About 12, 13% is the broken or worn scrolls internally. And then the last here, which equates to about 12%, is manufacturing nonconformance issues or motor issues. But that's a staggering number right there, that we replace compressors at a rate of almost 30% and they're not failed. So let's talk a little bit more about lack of lubrication. What does that mean? Well, it can mean that there's horizontal traps. We're trapping that refrigerant, that oil from migrating back to the compressor, or it doesn't have a proper vertical trap. How do we find out if we need these things? Well, we read the book. RTFM. Read that fantastic manual. Loss of charge. If we see that there's been refrigerant added to a system before, let's not just keep adding refrigerant. Let's actually find the leak if there is a leak. Or it could be due to us constantly connecting refrigerant hoses to the system. Little tip here on the side that I didn't put in here as well. It's not really ever the Schrader. It's not the valve core. We see far too often in our field and in the HVAC industry that people will charge it back up and say that they fixed the leaking valve core. How often is it a valve core on your tire? Yeah, it's usually not, right? It's usually leaking somewhere else. Again, it is not the valve core. Find the leak, let's fix the leak and stop this from happening, or we'll be replacing compressors. Short cycling. Oversized equipment. If it doesn't run long enough and it constantly short cycles, that is wear and tear on that compressor and can be lack of lubricating it. And oil dilution, which we kind of talked about earlier. So the flooded start or the liquid flood back. So understanding how to check your superheat and what that number should be, especially with the TXV system, and checking your subcool. You do not want liquid in that compressor. So when we start talking about lubrication, we have to understand the type of oils that are in these compressors and in these systems, and some terms to know. The first term to know is miscibility. And what miscibility means is it's the property of two substances to mix in all proportions, meaning they are forming a one solution. So miscibility is how well those two substances mix together, forming one solution. Viscosity. Most people know this, but the viscosity is the state of it being thick, sticky, semi-fluid in consistency due to internal friction. So it's the thickness of the oil. Hygroscopic. And what hygroscopic means is how well does it absorb moisture from the air? And hydrolysis. Hydrolysis is the chemical breakdown of that compound due to the reaction of that moisture or that water. So what kind of breakdown of that oil is going to occur, again, with reaction to water? And why it's important when we install these systems. So oil returns in HVAC system. Factors for good oil return in a system are oil and refrigerant miscibility, how well they mix. That's why there's certain, sorry about that there. That's why there's certain oils and certain refrigerants that we work with. It's because they mix well. Oil viscosity or thickness. It can be too much, it can be too little. Refrigerant velocity through the circuit. And what we mean by that there is proper sizing of the refrigerant lines. Depending on how long the refrigerant lines are, how much height they have to go, how much higher the coil is, the condensing coil is from the evaporator or vice versa. So we do have to consider the length, the rise, to get our proper sizing of the refrigerant lines. And the geometry of the refrigerant lines. Again, how they're running. So that length over rise, does it have to go up and then down again and back over and up another 20 feet? Know that geometry of those lines too if you're ever looking at a potential issue. So what are the typical types of oil? Mineral oil. What kind of refrigerants mineral oil in?
R22, isn't it?
R22. Yeah, that's our biggest one that we'll see mineral oil in. It's commonly used in CFCs and HFC refrigerants. So 22, R22. This mineral oil is not miscible with modern HFCs and HFO refrigerants. What's miscible mean again?
How well it blends if they make one.
How well it blends, exactly. So mineral oil used in HFCs, CFCs, R22, it's not miscible with our modern refrigerants, which is why when we go from an R22 to a 410 system, we want to replace that line set or clean that line set, replace it if all possible, but clean it if we can't. Alkyl benzene oil. We're not going to see much of this. This is a synthetic oil compatible with mineral oil. It improves miscibility at low temperature conditions. Our next oil is polyester oil or POE oil. What kind of refrigerant is POE oil in?
R410.
410A. It's the most common oil used in systems, again, with the HFCs and HFO refrigerants. And then we have PVE oil or polyvinyl ether oil. This is a synthetic oil that's being used as an alternative to POE oil. It's very, very common currently in ductless systems and VRF systems. In 2023, we're going to have a change. Okay. In Kentucky, the minimum SEER rating on air conditioners to be installed is going to be 15. In Indiana, Ohio, Illinois, some of the northern states here, word code is going to change from our 13 SEER to 14 SEER. There's also Puron Advanced is what it's being labeled as right now, and that is R454B. Right now, there's also other refrigerants out there too that Daikin and other manufacturers are using. So Carrier's plan, last I was informed of and educated upon, is going to be the R454B. I would bet that they're probably going to have this PVE oil and not the POE. But they haven't announced yet which oil is going to be in that refrigerant. So we shall see. So what is the difference of PVE oil versus POE oil? Well, both oils are hydroscopic, meaning that they both attract and hold moisture. Very important to properly evacuate a system, purge a system when we're installing. However, PVE oil is more hydroscopic than POE, so it's going to be even more important if we start changing to these PVE oils, especially, like I said, in our ductless and VRF systems. POE oil undergoes hydrolysis when it reacts to moisture. And what does that mean? Well, it means it actually decomposes into acids and alcohol. So having acid test kits and things like that on our trucks or in our tool bag is going to be nice, is nice to have, so you can actually see what's going on, especially when your compressor's, maybe tripping a breaker or something, or short cycling, something's going on with it. An acid kit is nice to have. Now, once this happens, it cannot be reconstituted within line or with line dryers or evacuation. So once you get acid in your system, it's a complete clean out. You can't just try to pull it out with your recovery machine and throw a refrigerant right back into it, because you're still risking that hydrolysis has happened and created acid within that system, which can lead again to compressor failures and other things. The PVE oil, even though more hygroscopic, it does not undergo this hydrolysis process with the presence of moisture. So it's more capable of being dehydrated again, unlike POE oil, which is good. It means that we are at less risk of creating acids in our system. So liquid refrigerant flood back. Liquid refrigerant returning to the compressor, which again, we don't want. We want a vapor fully returning to that compressor. Usually what will happen, or you'll see with liquid refrigerant flood back as well, is the metering device has lost control. So you'll see it constantly wondering if it's a TXV. There could also be poor airflow that could cause this, or heat transfer across the evaporator. And whenever the load is lost. So if it's not keeping up, then this is a thing that you can check within a home. There could be presence of liquid refrigerant flood back. So this is pictures kind of behind it here, but you can actually start to see with the flood back how it will affect the inside of the compressor. So these are just a few pictures here. Another term that we'll see is what we call slugging. Slugging is when refrigerant moves to the crankcase, initially as a vapor, and condenses into liquid form. The liquid refrigerant has a higher density than the oil, starts to rise in the compressor there. And at startup, the oil floating on the liquid refrigerant is pulled into the scroll flank up here which is going to slug that compressor, what we call slugging the compressor. So here's a picture showing what that slugging looks like on the inside of a compressor. How to prevent slugging? Well, how often do you guys check crankcase heaters out in the field? Be a good habit getting into. If it's got a crankcase heater, check it. Make sure it's working. If we think there's slugging going on, well, use a crankcase heater. You can install one onto a system. What that's going to do is warm the bottom of that compressor to keep that liquid and everything flowing properly in that oil with the right viscosity. Maintain proper system charge. Don't overcharge the system. Don't let it constantly be undercharged and you're adding refrigerant to it every 6 months. Maintain proper system charge. And then if we have long refrigerant lines, again, follow manufacturer specifications, especially when applicable. Let's look at some causes of overheating, some things that we can see out in the field. We call that high compression ratio. Okay, high compression ratio. You guys understand how to get how to get your compression ratio? Some nods maybe. Okay, we're gonna go over it. So this is what this is for here. So in air conditioning application, compression ratios are usually gonna be somewhere in the ballpark of 2.3 to 3.5 to 1. Those are our common ranges. With ratios below 3.1 or 3 to 1 and above 2 to 1 is standard for high efficiency systems. So again, if you're somewhere in that 2 to 1 to 3 to 1 ballpark, you're going to be okay with most high efficiency air conditioning systems today that we'll run into. How do you get that number? You take your discharge pressure absolute divided by your suction pressure absolute. So most people are like, well, what's absolute? I can get my discharge pressure and get my suction pressure, but what does absolute mean? It means this. Let's use this example here. You have 240 on your discharge pressure. You're adding your atmospheric pressure here of 14.7, or your absolute pressure, to equal your 254.7. We're going to use 75 on our suction side, and we'll do the same thing. Add that 14.7, and that equals 89.7 PSIA. You take your discharge absolute, divide it by your suction absolute, and you'll get your compression ratio. You can see on this example here, we're at 2.84 to 1. Is that okay? It's good. It's between our 2 to 1 to 3 to 1. So that is how we get it right there. So if anybody wants to write that down, take a picture, whatever you want to do with it. Your discharge pressure, absolute, divided by your suction pressure, absolute, will give you your compression ratio. If you have a high compression ratio, you're going to potentially cause that furnace or that compressor to overheat. Some more causes of overheating: high return gas temperature and or high superheat. So if you have a high superheat, are you low on refrigerant or are you overcharged on refrigerant? Probably a little undercharged. So you're having high return gas temperature getting back to your compressor. Scroll separation internally. Probably be able to hear that when it's operating. It makes almost sounds like a pressure relief valve. It's just hissing at you. And what you have to do at that point is cool that compressor down. Check that internal overload and make sure that it gets back within. You get continuity back through it before it comes back on, or before you try to turn it back on. It's just like a high temperature limit in a furnace. Undercharge or loss of refrigerant charge can cause overheating as well. Imagine running your car with no oil. You're going to overheat it. And here's what overheating looks like. Here's an internal overload. It's kind of melted. Once that thing melts and completely separates, compressor is done. And then here's the internal of a scroll and what it looks like, how it's starting to warp. You can see it there. Motor failures. Motor failures can be caused by non-condensables. What we mean by non-condensables is that it will not condense into a liquid within the operating temperatures of the refrigerant system. And you'll see your pressures wandering. You'll see your TXV in a system with TXV, you'll see it wandering as well. There could be foreign debris, copper flakes, etc., things like that. You know, we had an issue several years ago with TXVs getting stuck due to a foreign debris in the system. General burn. So usually entire windings burn. And what that can be from is voltage problems or lack of the motor being able to cool. You have a spot burn, which is a localized burn. That could be a voltage spike or foreign material on just one winding or one electrical circuit. Your start winding burn, only your start winding on that one. So that could be caused from a bad or faulty start relay, chattering of a contactor, could be a faulty capacitor working hard on the compressor, or outside of the motor, things that can add to that. And your leads could be shorted. So when you go to check a compressor, you check at the compressor, not the actual wires from inside of the service panel to the compressor. Always check at compressor. So here's a example picture of moisture and acid, and how they can tell that from the factory is you start to see this bronzing or this copper plating occurring from the acid. And then again, that's evidence of that acid or moisture in the system. Foreign debris, little flakes. See these little flakes here? That should not be in the compressor. Or burned windings. You can see they're all burnt here. So troubleshooting. If the system's not starting, what do we do? First thing that we always do is we always check to see if there's voltage. Do we have high voltage? Is the high voltage correct? Is the breaker tripped? Is the breaker on? From there, is the capacitor within specifications? Again, we're not going to be able to check it under load at this point. So what we'll be doing is we'll be checking it not under load to see if it's within specifications to at least start it. Contactor, does it have 24 volts to it? Does it have a call from the thermostat? Low pressure cutoff. So at that point, you've checked all these things, the capacitors within specifications. I've got high voltage. We've got low voltage at the contactor. The contactor is just not pulling in. Check the low pressure cutoff, high pressure cutoff, make sure it's not overheated. Check your high temperature cutoff on your compressor or any sort of time delay that you're just waiting on from the system, especially with these more advanced communicating systems. Suction and discharge pressure balanced. So if you do put your refrigerant gauges on a system at this point, if it's not starting, see if they're balanced, meaning equalized. They should be the same pressure on both sides. At that point, you can obviously tell if the pressure is low. And if the pressure is low, obviously we got other things going on that we need to check at and try not to start that compressor without figuring out a path moving forward. Ohm check. So compressor's not starting, all these other things are fine. We're good with it. Just like I was just talking about, take the top off, the fan off. Let's get to the compressor. Now we're going to check the windings of the compressor. And what are we looking for? We're looking run to common plus start to common should equal run to start. So what I mean by that is if you have run to common, it's 1.8. Start to common is 2.0. Run to start equals 4. It's close. We're right there within range. That's okay before we diagnose a compressor. Okay. What if it's starting though? Well, if it's starting, is it short cycling? Does it turn on and then shut right back off after so many seconds or a minute, 2 minutes? At that point, is it the low pressure cutoff? Does it have just enough pressure to start, hits the low pressure cutoff, and then shuts right back off? High pressure cutoff. Is it getting too much refrigerant in it? Do we have some flood back going on? Okay, or loose wiring. Does it trip immediately? So as soon as you turn it on, it trips a breaker. If that happens, again, we want to check our windings to ground and check our windings across one another. Does it have the correct voltage? High voltage, low voltage. Make sure they're all within the manufacturer range of their specifications, usually plus or minus 10%. Does it have the correct size capacitor on it? Is it undersized, oversized? If you're ever questioning that right there, you can always pull up, you can use an Emerson app and put in the model number of that compressor and it will give you all the information on it. Or you can actually go to your CE app or Service Tech app and type in the compressor model number, serial number, and it will give you that information as well. Is it noisy? What's it sound like? Is it the correct operating conditions? Is it 30 degrees outside and we're having some noise issues here? It could happen. Do we have a flooded start or flooded liquid back to the system, to the compressor? Well, how do we prevent these things from happening, right? So this will be our last little bit here. Correct equipment sizing. Very key. What we want is we want proper load matching on that piece of equipment, that AC. We don't want that short cycling. We just talked about it. That's not good for the compressor. Usually we follow manual J to make sure that we get the proper size for that load matching of the equipment for the home. Proper installation practices. And what we mean by that is use nitrogen when we're brazing, when we're purging. Make sure there's no oil traps in the refrigerant lines. Make sure it doesn't look like a roller coaster is what I like to call that. And make sure we get a proper deep vacuum. Make sure it holds that vacuum. Why do we want a proper deep vacuum? To boil out the moisture. We don't want moisture in that system. Again, depending on the oils and stuff, we don't want that happening. We don't want hydrolysis happening or the hydroscopic portion happening of that oil. Airflow. We always talk about it. It's not going away. It's never going to go away. Okay. Proper duct sizing. What's your static pressure? What's that motor doing? What's the airflow? Is it right for the system? We want approximately 400 CFM per ton on its design. And to do so, we follow a ACA manual D. Improper refrigerant charge. The coil type line set. How do we figure out how much additional refrigerant we need in it? We weigh it in with the weigh-in method. And then, of course, what we do is we validate and verify with superheat and subcool. And that leads to the end of our training today. What questions does anyone have? All right. Well, if you don't have any questions on here, feel free to contact me, get a hold of me, call me. Email addresses are there for you. I'd be more than happy to help diagnose, help go over a system with you, help walk you through it, especially if you have any questions on what you're working on in the field. Other than that, everyone have a great day.